Cool. Thank you, everyone, for coming. Thank you, Confluent, for inviting me to this talk. My name is Manpreet Singh, and I'm a software engineer at Yelp, and we maintain the Kafka infrastructure, and we provide a lot of abstractions, tooling, monitoring, automations on top of Kafka. At a larger scope, I am actually right now working in the stream processing team, and we maintain infrastructure around stream processing layers, which includes Flink, Kubernetes, Joinrace, Stream SQL, task processing systems, Spark on Kubernetes, and much more. And today, my talk will be focused on the challenges involved in upgrading large-scale Kafka upgrades. I have been involved in multiple Kafka upgrades over the past 4 years. Actually, working on Kafka for such a long time, sometimes I virtually feel that I'm working at Confluent. Just kidding. Oh, what's Yelp? Most of you are already aware of, but Yelp is an app and a website which aims at connecting people with great local businesses. Founded in 2004, Yelp has spanned over multiple countries across the globe. And today it has like more than 200 million reviews and millions of users. And to help Yelp achieve this mission, it requires a huge amount of streaming data, which today actually is all going through Kafka at Yelp. And my mission today here is to share you the stories, journeys, and the challenges which are involved in upgrading the large-scale Kafka upgrades, and how over the period of years we have evolved our upgrade process to overcome those challenges to make it a smooth, streamlined, and effective process. Now, to help achieve my mission, this will be the outline of my presentation. The first few minutes, I'll be spending some time on like why Kafka upgrades are important. Why do we need to care about this? And then I'll briefly touch upon the data pipeline Kafka infrastructure at Yelp, which is the data transportation mechanism. And then I'll be going through, iteratively going through the challenges involved in Kafka upgrades and how we have evolved our Kafka upgrade process, and briefly touch upon the Kafka on Kubernetes aspect, which we are currently working on. Finally, I leave some time on the questions. Now, whenever we do Kafka upgrades, we allocate this task to an engineer or a bunch of engineers at Yelp. And for the sake of the presentation, I'll be addressing those engineers as Kafka upgrader. So what exactly a Kafka upgrader does? A Kafka upgrader basically introspects the new and shiny, amazing version of Kafka released by Confluent, analyzes the business use cases, any kind of blockers in the way of upgrades, does all the relevant testing, and then smoothly integrates in our Kafka infrastructure. But why do we need Kafka upgrader at all? Before I go further, I just want to get a brief sense. How many of you folks have actually done at least one Kafka upgrade in their organization? Confluent, I'm sure like they are the pro in this field. Cool. And are there anyone who is using Kafka versions like less than 1.0, like the Kafka package version? The Confluent, I think, is probably 4.0 or 3.0. Oh, that's pretty awesome. There's also actually, so basically what Kafka Upgrader is doing, it's kicking out the older version of Kafka and bringing it the new and shiny version. I went too fast. But why do we need to upgrade Kafka? Actually, there is an amazing talk which I watched, the Gwen Shpiras from Confluent, her talk in the Kafka Summit in 2019. And I think it's a really amazing talk where she stresses a lot on upgrading Kafka clusters pretty often and showing some tips. But in regards to Yelp, one of the key reasons we want to upgrade Kafka is reliability. We know like none of the softwares are bug-free, and so is not Kafka. But every new version of Kafka, they bring with itself a lot of important bug fixes. And there is this one particular bug, which Kafka 2729, which was present in pretty much all the major versions before Kafka 1.1. And I can see some folks smiling. So I think I can relate the impact and the pain. This ticket had like a lot of watches and a long comment thread. I think multiple companies got impacted and Yelp was one of them. In this particular ticket, just to give a brief overview, the the controller broker lost its connection with Zookeeper. As a result, the new broker is selected as a controller, but the previous broker, when it comes back alive, it started acting as a zombie controller. As a result, it was sending update requests to Zookeeper and also the leader and ISR requests to other brokers, which obviously were failing because of the mismatch of epoch versions. And this is like very internal to the Kafka. And this is, I probably simplified a lot. The key thing is this had a huge impact on our multiple Kafka clusters, especially some of our Kafka clusters shared the same Zookeeper cluster. And that's why the impact was much bigger. And this actually became one of our key reasons for us to upgrade from 0.10 to 1.1 directly. So to summarize, sometimes Kafka upgrades are inevitable. We need to upgrade to keep our systems healthy and reliable. And most importantly, like we also don't want to stay behind too far and make sure we are picking up all the newer tickets. In fact, I was just doing a rough calculation from 0.10 to 1.1. There are probably like 1,000 tickets, which were either improvements or bug fixes. But is that reason good enough? Let's take a look. So this is my favorite reason. Every new version of Kafka, they bring with itself like a lot of new features, performance improvements, tooling improvements, metrics. And a lot of these features have a huge business value impact. Some of the features like the new consumer API coming in 0.9, it decoupled the consumer coordination from Zookeeper to Kafka, had a huge impact on the consumer performance and the reliability. Message timestamp coming in 0.10.2 message format is something we have been using in our connector ecosystems to upload messages to S3 or editing pipelines or even time-based offset management. Idempotent producer is well aware in the Kafka community, providing exactly one semantics is something we have been using in our Spark ETL pipelines, providing better production guarantees. And similarly, the latest one, 2.4, brought Mirror Maker 2.0, which I think was very well-awaited feature. So to conclude, a lot of the Kafka features really unblocks us for many of our business use cases, or even simplifies them or gives us better performance and better production guarantees. Now we have like established why do we want to upgrade Kafka. Let's take a look. Is it easy? So the typical Kafka upgrade process is like, in a simplified form, is pretty simple. You push the new version, which is basically either package version, protocol version, or message format version in the server.properties file. And then you rolling restart the cluster, which means you restart one host at a time. At Yelp, we use Puppet for deployment of our configs for our Kafka clusters. And expanding it a little bit more, a typical Kafka upgrade protocol process involves push the new version, new package version, rolling restart the cluster, push the new protocol version, rolling restart the cluster. As simple as that, right? It's like something we had been doing since we bought the laptops. Any new changes, restart the laptop, and it somehow magically, all the things starts working. Probably a bad joke. Now, what really stops us for upgrading Kafka clusters like that? Sounds like a fairy tale, right? Well, things are no longer simple when Kafka meets scale and complexity. There's nothing rocket science in that. It's like scale and complexity are very two common industrial paradigms for web-based, data-based, or app-based applications. And it's no different in case of Kafka, but let's try to understand what this really means in the domain of Yelp. At Yelp, over years, our data pipeline infrastructure, which is a data transportation mechanism, has really increased and covered a lot of streaming use cases, which today is all powered by Kafka. Some of the examples are our indexing pipelines. Powering user search is on top of Kafka. Many of our purchase flows is powered by Kafka. A lot of the ad analytics, real-time ad campaign shutoffs, ad acknowledgements, it's all today is powered by Kafka. A lot of ML features are computed real time, then stored onto Kafka, or maybe computed by batches and then stored onto Kafka. And then we have a connector ecosystem which uploads those features onto the desired data stores, being it Redshift, Cassandra, S3. And then on top of those, the user personalization models could be run to give the more personalized results for the Yelp app users. Similarly, our experimentation frameworks, logging infrastructure is very, very strongly dependent on top of Kafka. All in all, today, Kafka is the core of our infrastructure. Now, to support all these kind of business data pipeline use cases, the underneath Kafka clusters, we have like more than 40 Kafka clusters providing different ordering, compaction, message delivery guarantees with different various loads. And on top of these Kafka clusters, we have like more than 50 terabytes of data going through it per day, and much more than 125 plus billion messages going through it per day. This is a bit old calculations, so it should be much higher now. These producers are also providing different ordering and message SLO guarantees. And not just that, there are many of our producer and consumer client libraries are implemented in different languages like Java, Python, and we have like open source systems like Apache Flink, Apache Spark, Apache Beam, which is running on top of Kafka. All in all, making it a pretty complex infrastructure. Now, when we have that level of complexity, then we kind of can conclude that the Kafka upgrades, it brings out a lot of challenges in Kafka upgrades. Now, before I take you to the journey of Kafka upgrade challenges, so this is a brief timeline of Kafka upgrades at Yelp. Starting in 2015 with zero-rate Kafka, we pretty much have upgraded more or less one Kafka upgrade every year with the 1.1 message format in 2019. One key thing to notice, like we directly jumped from 0.10 to 1.1 for the critical issue we had in 2018. Now, why I was showing this slide? So when we have like those many upgrades, that means it requires a huge amount of engineering investment, and which eventually means from the business perspective, a lot of engineering cost. That, and this is one of the statistics which I calculated. On the left, the columnar chart on the left is roughly the time taken for end-to-end upgrade, which includes testing, clearing blockers, upgrading Kafka clusters. The right-hand side columnar chart is just the actual upgrade time. I'll explain later like why two separate charts make sense. Also, just to keep a note, that doesn't necessarily means that it took like 7 months or 6 months, because an engineer can be working on multiple projects, or there may be a baking period between Kafka cluster upgrades. But for the key takeaway when I was building this chart was, even if our scale and complexity was increasing, our overall upgrade time was more or less decreasing. Now, that's how were we able to achieve that. So the next few slides, I'll be taking you to our journey of the first big challenge, which is controlling the engineering cost, and what kind of automation tooling we have built on top of Kafka to make the Kafka upgrade process much more cost effective. So in the earliest times, we started with writing this Kafka rolling restart tool, which is currently open sourced as part of Kafka Utils library. And it's still pretty strong. And what that tool is basically doing is, after restarting a host, so it's a manual tool. When you run that tool, after restarting the first host, it ensures that the cluster is healthy, which primarily means that the Kafka process is running successfully after the restart. And also the under-replicated partitions have gone down to 0 before moving on to the next host. So this was our starting point. It's a pretty good tool, but some of the limitations were, since we use Puppet for deployment, it sometimes becomes hard to track whether the new config or package versions have really been deployed or not. So there are a couple of ways around, but all of them are manual. And this especially becomes more difficult when you have like larger Kafka clusters with 30 plus brokers. And if for some reason during the upgrade, your upgrade process fails, you have to like keep track of which brokers have started or not. So we improved this tool in our future versions of Kafka rolling restart tool, wherein we have a pre and post checks before restarting the host. The pre-check was basically we check on every host whether the new version, which is like package version or protocol version or message format, based on the requirement at the time, has been deployed on that host or not. If not, it will automatically deploy it and then restart the host. If it has already been deployed, then it goes ahead with restarting the host. So this made the upgrade process faster than the previous version, but this still had many limitations. And some of those limitations are characterized with the characteristics of this rolling restart tool. The first, it's like manual tool. The Kafka upgrader has pretty much has to sit through the rolling restart process. They can actually work, but it's still to keep an eye if cluster is upgrading smoothly or rolling restarting smoothly or not. Secondly, even the monitoring was quite manual, just to keep an eye if things got stuck or not. Especially during the upgrades, we want to catch any kind of issues or errors much sooner than later to minimize the impact just in case. And most importantly, we could do only one cluster at a time because the manual tool was limited to one cluster. One could do multiple clusters at a time, but that means more manual effort in parallel. But once we know the limitations, we can start thinking about the improvement strategies. And this is how our upgrade timeline looked pretty much, coming back to the original chart. The push process, I kind of put it like more or less 30 minutes, which is like putting a review, getting reviewed and pushing it. The automated part is the Puppet deployment, and then the rolling restart, which for the smallest clusters I've seen like as low as 5 minutes to one of our biggest heavily loaded clusters with compacted data. I've seen like around even up to 6 hours for the whole rolling restart. And similarly, the same cycle for protocol upgrade. And you can, if you try to summarize all the minutes, that comes out to be pretty high. And this is going back, and this is something we were using for 0.9 and 0.10 upgrade. To putting into our big O notations for calculations purposes, let's say our Kafka ecosystem has k Kafka clusters with an average of B brokers. What that means is it more or less will take order k into B time. Also, just to share the experience we have observed, if the load on the brokers or the Kafka cluster is pretty heavily loaded, the average time per broker is something we have seen also increases. I guess Kafka 2.3, I think they have improved the broker restart times, making it independent of the data size, but I might be misunderstanding that. But now we know that K and B are both variables. That means we know what variables we can try to control when we can think of the automation, which is something a very common word which we use when we have to make sure how we can reduce the redundant steps or repetitive steps. Maybe we can reduce it to order K, order B, or maybe order 1. Let's take a look. So we built this system. It's something we called as acronym KCAD, the Kafka Config Auto Deployer, which, as the name suggests, it automatically deploys the new configs once it detects that without any interference or manual intervention by a Kafka upgrader. Now, to go a little bit deeper into architecture of this, it primarily is divided into 2 parts. The one on the left is something we call as Taskerman, which is the task manager. The Taskerman basically orchestrates the cluster-wide operations like repairs, reboots, or restart in a very safe and reliable manner. And the way it is doing is it's sending the restart tasks to the Amazon SKS queues. Taskerman uses Zookeeper for coordination. And now that very much maps with our Kafka use case because Kafka also uses Zookeeper for coordination. And in case of Kafka also, we want to restart one host at a time. So that really mapped with our use case. The Taskerman was also used for other clusters like Elasticsearch, Cassandra. So it's it's kind of a template thing being used for other clusters. And inside the Kafka clusters, where I notated brokers as B0, B1, B2, where the KCAD is running as a cron job. And that basically enqueues those tasks, restart tasks, and restarts the hosts if it detects any config change. Going a little bit more deeper, the simplified architecture of Taskerman, it is a task scheduler which submits the restart tasks for every host of every Kafka cluster in our Kafka ecosystem it uses the AWS stacks in our case to identify the right host of right Kafka cluster in the region. So it submits in the Amazon SQS queues. And then the KCAD, which is running as a cron job in Kafka nodes in brokers, enqueues those restart tasks, coordinates with Zookeeper to acquire the lease, and then restart the host. So that's from Taskraman perspective, but let's go a bit deeper from the Kafka cluster perspective. The Taskraman client submits the periodic restart tasks for every Kafka cluster and every broker. Going inside Kafka cluster A, these three brokers, they pull the restart tasks from Amazon SQS queues, and they will try to acquire the Zookeeper lease. One of the brokers will succeed in acquiring the lease, which is essentially a lock. And once it acquires a lock, it's going to verify if there is any config change. The way we do it is we check the SHA of the file. And if any of the parameters in the broker configs, like message format, protocol, or even message size or other parameter changes, it identifies as a valid config change. Then it restarts the broker. And the rest is more or less similar to rolling restart tool. Waits for cluster to get stable, sends the complete event, and then releases the lease. Similarly, other brokers eventually acquires the lock and restarts their hosts eventually. And all of this is being done automated. The only thing which a user has to do is push the config. And not just that, we also automated our alerting and monitoring. The KCAD is also sending the broker start, stop, successful start, fail start events to the SignalFX. And we also get alerted in case something goes wrong so that we can take actions as soon as possible. Coming back to our timeline chart. So KCAD, what KCAD basically did, this converted this manual step of rolling restart into automated ones. So the only manual steps which were left is the config pushes. And to summarize, KCAD basically reduced the Kafka upgrade process to a single push button, which is just a config push change. And this is something as a newer Kafka upgrade process evolvement, which we are currently developing and in progress is we are moving on to Kafka on Kubernetes. And Kubernetes has its own features to restarts their pods, which is essentially the Kafka host in this case. The mechanism is very similar to KCAD, but this is like the future of upgrades. One, the key differences with Kubernetes and the KCADs is one, it's internal features of Kubernetes. We just need to use calculate the pod spec where we attach the different environments, in this case, the Kafka versions. And second big difference is the deployment part. We use our platform as a service component, which reduces the deployment from like 150 minutes, which we have seen in case of Puppet, to like order of few minutes, maybe 2 or 3. The 30, I just put it as like review, adding a review, getting it reviewed. So that's the next feature of our upgrade process. Coming back to KCAD, so the upgrade time, we started with order K into B with rolling restart. And with KCAD, the upgrade time is actually still the same because it still has to rolling restart. But the engineering time is, theoretically, it has reduced to order 1 because now it's just a config push. However, practically, that would be quite risky to upgrade all our production Kafka clusters at once. We still try to plan and span our Kafka upgrades for production clusters over the period of days, depending on the priority of cluster, depending on the production guarantees of the cluster. And so I put it as like order of K dash, which could be anywhere from 0 to K. The less the issues, the higher, the lower the K dash can be. And this is putting into a numbers perspective. Without KCAD, we probably had seen like our upgrade engineering time could go up to like 240 hours for our 40 Kafka cluster ecosystem. But in our most recent Kafka upgrades, we saw it being reduced to like less than 20, 30 hours. So that's a big win when it comes to upgrade process. To summarize, KCAD automated the rolling restarts. It bettered our monitoring and alerting. And we could do multiple Kafka clusters at once, and which we actually used because as we build confidence. And most importantly, why to limit KCAD to just restarts? We could extend KCAD to other operations like reboot. This is something we did when we had to do kernel upgrades for our Kafka hosts. So that's additional features of KCAD. And that was a good win from engineering cost perspective. But is that challenge enough? Let me take you to the journey. Time for a story. So let's see how much time I have left. So in one of our Kafka upgrades, we were upgrading from 0.9 to 0.10. And when we upgraded some of our clusters, we started noticing that the consumer offsets topic, which is storing all the offsets of all the consumers, the log cleaner has stopped working to compact the consumer offsets topic. Now, as a result, it was increasing at a speed of 100 MB per second. We tried to mitigate this, and we also found a well-known upstream issue with 0.10 exact issue. So we decided to roll back our clusters to 0.9. However, in the middle of the rollback, we noticed that one of our very critical task processing consumer lost all its offsets. As a result, it started processing more than like 10 million tasks again, causing delay in the task processing pipeline. And while we were trying to advance the offsets and understand more of that issues, we noticed that one of our critical Java producers, which at the time was producing most of the traffic, also crashed and failed producing. With some firefighting, we were eventually able to fix and mitigate the issue and fully roll back our clusters to 0.9. However, this was a huge setback for our Kafka upgrader. And also, a lot of learnings and lessons for our Kafka upgrader. One of the key learnings was we realized that it's not only important for us to test the upgrade strategies, it's equally important for us to test the rollback strategies as well. And secondly, if we can devise a plan to get exhaustive cases of tests which we could do. Now our Kafka upgrade came stronger than ever. And that brings us to the next big challenge, reliability. You may recall, like in the initial slides, I mentioned that we wanted to upgrade from 0.10 to 1.1 because of one of the critical bugs in the Kafka ecosystem. However, imagine like we upgrade our clusters and we have even more reliability issues. So it's kind of a deadlock in our goals. So it was very important for us to make sure that we have enough testing being done when it comes to reliability of our data pipeline ecosystem. Now, so this is, again, maybe a funny animation, what this really means. We upgrade the Kafka, and there's a fire which spans onto the whole data pipeline ecosystem. Nobody loves that. And it's also not just impacts the business or the ecosystem, but also has a huge impact on the Kafka upgrader. That brings us to the second big challenge, which is reliability. And one of the key things which we did, we broke down the complexity of our data pipeline ecosystem into few important layers. Some of these layers are upgrade mode, which is like upgrade and rollback. Client types, producers and consumers, or even like older and newer producer consumers. Languages, important client versions. And most importantly, this is the most important, this list of scenarios. As in like when to start the producer, when to upgrade, start the new consumer of the earliest offset, latest offset. And once we have this test plan, we built a test suite wherein we ran the producers and consumers for a given scenario in the Dockerized environment for our test clusters. Now, this is also to keep in mind, like building that test plan is itself quite challenging because we want to make sure we want to cover as much cases as possible, but we know in our Kafka ecosystem, there are like thousands of cases. So it's really hard to cover all of them. So we need to keep the cost-effective engineering cost in mind as well. Now I'll take you through one such specific test case. We started a Kafka producer, which is the newest Kafka producer. and started producing onto the 0.10 Kafka cluster. This is the initial state. This is one such scenario. And then we upgraded the Kafka clusters to 1.1 protocol and 1.1 message format. And then we rolled back the cluster to 0.10 because you never know, we may have to roll back. Now, we started a new consumer with using one of our very commonly used Kafka Python libraries with version less than 1.4.2. Now, when we started that consumer with the earliest offset, we noticed that the consumer crashed consistently. Now, as edgy case as this may seem, this is actually a very common use case if we had to roll back our cluster. And it was a really win-win situation for us to find this use case to help us make our upgrade decisions much better. So what we ended up doing was, from the initial state in 0.10, for existing clusters, we decided to upgrade to 1.1 Kafka and still keeping the message format as 0.10. That enables us to get rid of the critical bug. However, for newer clusters, we decided to go ahead with 1.1 message format so that we can unblock the use cases of using the exactly once production semantics. And this is actually was at the time used for Spark ETL pipelines. And for existing clusters, then we can go ahead with upgrading all our Kafka clients to Kafka consumers greater than 1.4.2 before going ahead with 1.1 message format. Now that was our plan. And now it was time for the D-Day for Kafka Upgrader. Let's see what's the result of reliability 1 or 2 in our next Kafka upgrades. So when we upgraded from 0.10 to 1.1, apparently we did not have a single major fire because of Kafka upgrades. And not just 0.10 upgrade, even with 0.10.2 message format upgrade, we also didn't have any major fire. So that was a really big win for a Kafka upgrader. There were other reliability efforts which goes, test suite is one of them. Other reliability efforts goes into like benchmarking, performance testing, message duplication, message corruptions, message missing messages, testing basically data SLOs. We also planned a lot in spanning our upgrades into the right time during the day so that whenever our critical batches run, we make sure we are not overlapping with them. And to conclude, test suite basically fulfilled all the 3 important paradigms of testing. They made our Kafka upgrades much more reliable. They made it much faster. And most importantly, the short-term investment to build the test suite and the test plan paid us in the long term as being reusable. Okay, I missed that slide. There is one interesting story with our 1.1 message format upgrade, which we did in the end. All our Kafka clusters were successfully upgraded to 1.1 message format, barring one cluster, which is one of our very important clusters. And it was very interesting to see that it's in the notes of 0.11 message format, wherein the Kafka, without going into too much detail, Kafka treats the batch of messages as a single message, and as opposed to the older versions where it treats every message as a single message when it comes to comparing with the max message size for producer and the consumer side. And if any of the producer or consumer clients are using the older versions, and if the message max size, which in our case is defaults to 1 MB exceeds, the producer will start crashing. One of our very important producers was using the older clients, and few of the message batches exceeded the 1 MB size. And we had to roll back that cluster to 0.10. But the good thing was, because we had upgraded all our consumers to 1.4.2, the rollback actually was successful without any issue. Otherwise, we could have potentially lost a lot of consumer offsets for all the consumers falling into this edge case. This is just to share that it's very hard to cover all potential cases. We could only do the best we can. And the good thing was we did not have any kind of business impact except some amount of delay and the effort spent into upgrading and rolling back. And now we have a plan to upgrade that critical important producer to the newer version as well. before we go ahead with upgrading our last cluster. So that's another good win when it comes to reliability. To conclude, Kafka upgrades can be really challenging and daunting. However, considering the importance of upgrades, we should not discourage ourselves. And with the right amount of effort in the reliability and in the automations, Kafka upgrades can be done in a very smooth, reliable, and effective, streamlined way. Thank you.
Thank you, Manpreet. Any questions?
For upgrading zookeepers, we did not have to do any. Oh, okay. So when in the domain of Kafka upgrades, we did not have to do any kind of zookeeper upgrades. But I think if I remember correctly, the bug which I shared, Kafka 2729, it had one of the improvements it had was using the latest zookeeper version. And I think for that, maybe in parallel, we had to upgrade our zookeepers by a different team, but I don't exactly remember. I can help you confirm, but on the top of my head, like we definitely didn't have to do any kind of zookeeper upgrades.
Is the test harness open sourced as well?
No, right now it's not open sourced, but once we go ahead with Kafka on Kubernetes, so even with Kafka on Kubernetes, we still have to use the test suite because it just changed the process. We may come back and decide and improve it and open source it.
The Kafka broker configurations, are these Docker images or?
The Kafka configurations are, they are not Docker configurations, but they are very specific to the Kafka configurations.
I meant Docker images.
Sorry, what's your question?
Are all these brokers running as basically it's same image of a replication of a Docker image, or?
No. The Docker images was just set up for testing purposes, but we don't run Kafka in Docker images. In Kafka and Kubernetes, we would be running because that's the concept. But right now, it's installed as a standalone process on every host. Does that answer your question? Okay.
Any more questions?
Right now, we don't have any specific configurations. All our configurations are on top of our data pipeline ecosystem, the data pipeline libraries. I think so, but yeah, I need to double check again.
Okay, and maybe I can ask a orthogonal question. Maybe irrelevant to upgrading. So you mentioned that at Yelp, you have like 40 plus clusters. I'm wondering, what do you make decisions about adding new clusters versus like scaling out existing clusters? Is that based on usage or is that based on capacity, things like that?
That's a great question. So the short answer is it's both of them. There's an abstraction layer on top of Kafka at Yelp. So we basically, in the long term, we have plan, which currently we are already doing a lot, to divide clusters based on priority and policy. When I say priority, as I think one of the persons was asking client quotas on priorities, so we try to give dedicated clusters to a very high priority streams, for example, ad streams. And policies are basically our production guarantees, like if we want to give more consistency or more availability. So that's where adding more clusters come if our business use case is inclined more towards a category of priority policy. Now, within the priority policy, our first goal is to scale the cluster as much as possible. And in the scaling of clusters, we go twofold. One, scaling the disk space if the shortage is the disk, or maybe using the better instances. That's our first preference. And the second preference is like scaling the number of instances. Does that answer your question? Cool, thank you.
I have a question. You said you do not use Kubernetes to run Kafka brokers, but if you did, there is Kubernetes operator by Confluent. Do you know if it was the case, would the upgrade experience be any different than yours? Like, can the Kafka operator simplify the process you have to go through?
Yeah, great question. So so the Kafka operator development and Kafka on Kubernetes is very actively in progress. So we very soon plan to start using Kafka on Kubernetes. And regarding the upgrade process, you asked like whether it will improve. So it is definitely going to replace KCAD because of the concept is very similar. But we are going to use the philosophies we used in KCAD, very similar in the module which we are going to develop inside Kafka and Kubernetes. But from the reliability and testing perspective, in my understanding so far, I don't think it will make any changes because the complexity on top of Kafka is still the same and we still need to do tests. But definitely it's going to improve in the speed of upgrades and we don't have to maintain a separate system. Does that answer your question?
Entirely. Thank you.
Cool. Thank you.
Cool. Any more questions? Oh, okay.
So you said the Taskerman in KCAD, it talks to Zookeeper to schedule the upgrade, right? And then each broker to perform the rolling restart.
So Taskerman is essentially just submitting the restart task to Amazon SQS queue. And then on the Kafka broker, the KCAD process is running as a cron job. Now, when the KCAD process runs, it's going to pick up that tasks from the SQS queue. And now the Taskerman is not exactly in picture, but it's still going to use templates of Taskerman. But what it's going to do, the cron job itself, the KCAD process, it is going to try to acquire the lease from Zookeeper. So that's, so this is, in this KCAD, we call it as a task runner. Okay. One of the components of Taskerman. And the KCAD is going to acquire the lease. If it gets the lease, it's going to check, oh, there's a config change. Let me restart the host. It restarts the hosts and then gives back releases the leak.
Okay, so most of the time, this will all be dependent on Zookeeper. But in like future releases, Kafka is still planning to keep Zookeeper as separate and like you can run without it. So do you think that will be a huge change for your flow or it will be still the same?
Yeah, that's a really great point. Kafka is planning to get away from Zookeeper. If at the time we are still using KCAD, that will be a drastic change. I'm not fully aware of the internals, how the Kafka on Kubernetes is being implemented right now. But if it is not using its interaction with Zookeeper, then it wouldn't be any change. But if it's using, then it has to figure out some other way to acquire the lock. So the only where the Zookeeper is being used is for the coordination to acquire the lock so that we can ensure that only one host is restarting at a time.
Oh, okay.
That's the only purpose.
Okay. Thanks.
Okay, let's thank Manpreet again and thank everyone for attending tonight's event.
Thank you everyone for coming, and I would love to talk with you guys.
Yeah, both the speakers will stay. So if you have more questions, feel free to reach out to them. And our next event will be in April. So if you have not, please register at meetup.com or join our Confluent community Slack channels where all the meetup information will be shared there. Thank you, everyone, and good night.
Thank you.